Everyone, and welcome back to Easy Taleem. Today's chapter is one of the biggest turning points in AS mathematics. Up until now, mathematics has mostly been about algebra, functions, quadratics, coordinate geometry. Today, and also maybe the last topic that we did of circles, geometry and algebra finally meet, right? But before we calculate a single arc length, and we will discuss what an arc length is, but if you have already done um, your O levels or GCSE, then of course you do know what an arc length is, right? So if I construct, if I construct a sector, right? Then this part of the circumference, between these two radii, this part I'm talking about. So this part is the arc length, which we denote by small s, and we will discuss about, and also not just discuss, we will derive the formula, right? But however, before we calculate even a single arc length, which is r theta, before we even write a formula, I want to answer a question that almost nobody asks, and hence do all this stuff randomly. Why did mathematicians invent radians in the first place? All this entire chapter is about this unit of angle, right? Now, because if you don't understand that, then every formula in this chapter feels random. But if you do understand it, then almost every formula in this chapter becomes obvious. So today, we are not memorizing, we are deriving. Now, in this lecture today, we are going to cover why degrees are actually inconvenient. We used to do 360 degrees in a circle, right? Everyone knows this. We are also going to discuss what does 1 radian mean, right? We are also going to derive that why is pi radians equal to 180 degrees, equivalent to that. Now, why Cambridge almost always prefers radians, right? And not just Cambridge, mathematics prefers radians. So in the next lecture, we will derive why the formula for the arc length is s is equal to r theta, where theta is in radians. And we are also going to derive the formula for a is equal to half r square theta, where theta again is in radians. Although these derivations are very simple, but still. So instead of memorizing them, everything today builds towards those formulas. So let's draw a circle. Right here we have a circle. Yeah, nice circle. Now, who decided there should be 360 degrees inside a circle, right? Now, the earth doesn't care, the moon doesn't care, physics doesn't care that there should be a total of 360 degrees, or this circle has to be divided between 360 equal parts like this. So if I make a lot of parts, so nobody, so who decided that there should be 360 equal parts inside a circle, right? So someone thousands of years ago simply divided a full turn into 360 equal parts, right? Now, could they have chosen 100? Of course. Could they have chosen 720? Also yes. So degrees are simply a convention. Mathematics prefers something much more natural. So now 360 degrees, then one full revolution, then one full revolution is going, so in an entire revolution, what never changes? So this circle, in this entire revolution, if I go, so wait a second. So if I go from here all the way to here, what never changes? This circle never changes, right? So instead of measuring turning, what if we measured the angle, right? Using the circle itself. And that's exactly what radians do. So now, let's say that this center is O. Let's say that this point is A. Let's say that this point is B, and you already know that both of them, so this is radius, and we can make a chord, let's call it chord AB, right? Now, what if this curved arc from B to A or A to B, however you call it, what if this one is also R, right? And we are saying that this curved length is also same as r, the radius of the circle. So we are not saying that it should be twice, we're not saying that it should be half, exactly equal. So we are saying that the arc length AB is equal to the radius of the circle. So this angle right here subtended at the center is called 1 radian. So this is the convention for radians, right? So again, a radian is not a distance. A radian is still an angle. It is simply an angle defined using the geometry of the circle, that if if AB, so if the circle has a radius r and this arc length between A and B is of the same length as the radius of the circle, then we say that the angle subtended between A and B at the center is 1 radian. Okay. Now, if I make the circle larger, does 1 radian change? So if I just make a circle larger, is this going to change? Wait a second, let me show you. No, this is not going to change. We're just going to extend this, right? And how are we going to extend that? We are just going to do it like this. Wait a second. So did you see that this angle remained same? It didn't change, right? Now, if I make a smaller circle instead, let's do it like this. Now, does this angle change? No, it does not change. It is still the same, right? So the arc gets longer and also the radius gets longer, right? But the angle stay equal. So the angle remains exactly the same, and this is why radians are independent of circle size, and so is degrees as well. Okay, so there is no distinction there between the two units. Now, let's say that the entire so you did that the circumference of a circle is equal to 2 pi r. Okay, now if 1 radian corresponds to 1 radius length, so 1 radian is for 1 radius length, right? Or 1 r centimeter, right? How many radians fit around the whole circle? Okay, so this is a question that I want you guys to think in your head. Okay, so we are saying that if sorry, this doesn't look like a circle. Probably this one does more like it. Okay, so what we were saying was that if, wait a second. So if this is r and this is r, so how many such radius can fit in one circumference, right? So circumference is 2 pi r. This length is r. So how many such lengths will be there? So we divide it by that. Okay. So we are saying that then that's going to be 2 pi of them, right? So if there are going to be 2 pi of such lengths, then there are going to be 2 pi of such radians as well, right? So now if 1 radian corresponded to 1 arc length, right, which was equivalent to radius, and there are 2 pi of such radius in one circle, then there are going to be, because it corresponds directly to the arc length, then there are going to be 2 pi radians as well inside a circle. Now 2 pi radians is equal to or is equivalent to 360 degrees. Then we say that 1 radian is equal to 360 upon 2 pi degrees, or we can say that this is equivalent to 180 divided by pi degrees. Okay, so there you go, right? So this is how we so nobody assumed that 2 pi, that 1 pi, and also vice versa, pi radians is going to be equal to 180 degrees, right? So nobody assumed. We just took the convention that if 1 radian corresponded to 1 arc length, right, which was equivalent to the radius, right, and there are going to be 2 pi such radius on the circle, so 2 pi r divided by r is same as the number of the radians inside a circle, and there are 360 degrees, or so they are equivalent units, right? Therefore, so in a quarter circle there is going to be pi by 2 radians or 90 degrees. In a semicircle there are going to be pi radians or 180 degrees, and in a full circle there are going to be 2 pi radians or 360 degrees. So this is not something to memorize. We have literally derived it from the definition. Okay, so now in order to convert from degrees to radians, right, what do? So we already have this, that pi radians is equal to 180 degrees. You can make a few variations of this. Divide both by 180. So this is going to become pi upon 180 radians is equal to 1 degrees. Now, and also divide both the sides by pi. So you will get 1 radian is equal to 180 upon pi degrees, right? Now, if somebody asks you, let's say you ask me what is 72 degrees equivalent to. So if I want to find 72 degrees, I will multiply both these sides by 72. So 36 times 5, 36 times 2. So this becomes 2 upon 5 pi radians. So this is equivalent to 72 degrees. Now, if somebody asked you what is 3 upon 2 pi radians equivalent to, right? So all you're going to do is you're going to multiply this 1 radian by 3 upon 2 pi. So this is going to become 3 upon 2 pi radians. And if you're multiplying it on the left hand side, you must do exactly the same on the right hand side as well, right? So pi cancels pi, 2 cancels this. So 90 times 33 is 270 degrees. So 3 upon 2 pi is equivalent to 270 degrees. Okay. So that's it. Now, if I ask you what 45 degrees is going to be, using the same, you will tell me that this is equivalent to pi upon 4 radians. If I ask you 30 degrees, you will say pi upon 6. 60 degrees, you will tell me pi upon 3 radians. Okay. So it is as simple as that. You don't have to memorize it. You can all the time you can derive it, but you will only be able to derive it properly if you do good practice, right? And you can go to your Cambridge book and start doing the first 2 exercises of your circular measure chapter, which probably is the 4th chapter in your Cambridge endorsed black book cover book. Okay. Now, Cambridge loves exact answers. Never write 3.14159 for the value of pi. Never do that. Okay, unless you're asked specifically to leave your answer in 3 significant figures or 4 decimal places, etc. Leave pi in your answers always. Now, if your answer is 30 degrees and you're supposed to give it in radians, just write down pi upon 6 radians, right? If you're supposed to leave your answer in 150, so this is what? So this is 60 plus 90. So pi upon 2 plus pi upon 3. So this is pi upon 3. So this is 5 upon 6 pi. Okay, 5/6 of a pi, or 5/6 of 180 degrees. Similarly, for 225 degrees, this is just going to be 5 over 4 pi. And you can do that in your calculator as well. For 330 degrees, because 30 is equivalent to pi by 6, so this is going to be equal to 11 upon 6 pi radians, right? So I'm stressing exact values here because this is going to come in handy. Now, don't memorize conversion, use proportions. Okay, so that's your first shortcut. The way I was doing here, I was making use of proportions, that if 100, so if this is 180 and this is equivalent to pi, so 150 is like 5/6 of this entire thing, so I just put 5/6. Similarly, if this is 360 and this is 330, so this is 11 upon 12, so I will just write the, oh yeah, so this is 11 upon 12 of 2 pi of 360. So 11 upon 12 of 360, or 11 upon 12 of 2 pi, because we are doing radians. So now this cancels this, so you're left with 11 upon 6 pi. So we are doing proportions here, right? We're not memorizing conversion. Now think in fractions of a circle all the time, right? So 150 degrees. Okay, let me just try to make a nice circle here. So 150 degrees is going to look something like this. So if this is 150 degrees, so this is what proportion of a circle? So this is 5 upon 12 of a circle, and circle has 2 pi radians, so this is 5 upon 6 pi. Okay, so this angle is going to be 5 upon 6 pi, because 1 radian corresponds to 1 arc length of r centimeter, right? Now, always simplify pi fractions. Do not leave it like 5 into 10, so 10 upon 12 pi. Do not do that. Make it look nice, 5 upon 6 pi. Never use calculator, because if you put it in your calculator, a lot of times your scientific calculator leaves the answer in exact forms. But if it doesn't, then you're, I don't want to say it, but you're screwed. Okay. Now, shortcut number 5 is that you must recognize common angles instantly. So multiples of 30. 30, by the way, is pi upon 6. Multiples of 60, which is multiple of 30 again. So this is pi upon 3. Multiples of 45. 45 is pi upon 4. So 135 is going to be 3 pi upon 4. 225 is going to be 5 upon 4 pi. 315 is going to be 7 upon 8 pi, right? So make sure that you recognize those common angles instantly. Now, I want you guys, I'm not going to do a lot of practice questions here. I've already done quite a few here. I want you guys to go to your books, do those first two exercises in your Cambridge endorsed book. It's going to help you recognize the pattern and also build muscle memory in your fingers and in your brain, that whenever such a question comes, you can recognize how to convert it instantly. Because whenever this chapter arises, or whenever in trigonometry you are given a range that x lies between, you're accustomed to seeing ranges like this in trigonometry, but now in circular measure and in trigonometry as well, in AS level, you are going to be given, sometimes you will be given domain in 2 pi. Then also we are going to discuss that how you convert your calculator in the radian mode. So you have a button there up there, so you go to your mode or in the calculator, and in degrees you have two options, so DEG or RAD. So whenever you see something in terms of pi, you must know that they're discussing radians, right? So always the first thing that you must always do is put your calculator in the radians mode, because 10 2 pi is going to give us 0, right? Okay, so 10 2 pi in radians is going to produce a 0, but 10 2 pi in degrees is going to give you a value for 10 of 6.26 something, 262 something, right? So this is going to give you a positive value, because the curve is going to be something like here. So a value very close to 0, but nonetheless a positive value. However, in radians, this is going to be an absolute 0, because 10 2 pi in radians is for 360. So 10 curve goes like this. So this is 360 or 2 pi. So 10 of 2 pi is going to give you a 0. Okay. Now, in this lecture, we answered a question that almost nobody asks: why radians exist, right? Now, something beautiful happens, because in a few minutes, we will derive every famous formula students usually memorize. You will finally understand why the arc length S is equal to r theta, and why the area of a sector is equal to half r square theta. And you would understand this arc length, you did theta upon 360 into circumference, which was 2 pi r. So this is just proportion of the circumference, and area was theta upon 360, where theta was in degrees, and this theta was also in degrees. So theta upon 360 into pi r square, right? Which is again the proportion of the circle. This corresponds to the proportion of a circle that we are considering for the sector. Okay. And we are also going to see in this lecture only that why Cambridge insists on radians instead of degrees. So once you've seen those derivations, circular measure becomes one of the most logical chapters in the entire syllabus. So if this lecture, by the way, is helping you understand why instead of just what, I urge you guys to subscribe to the channel, share it with a friend and who's preparing for 9709, and let me know in the comments that what surprises you the most about radians. Let's start the next section. Now, I want to show you something that degrees can never do. Until now, we have only changed units, degrees to radians and radians to degrees. But why did mathematicians abandon degrees in higher mathematics? Let's do that, right? Now, because radians remove unnecessary constants. Okay. Now, circumference is what's happening? Wait a second. So, circumference is 2 pi r, right? Now, an entire angle in the circumference is 2 pi radians as well, right? Now, so 2 pi radians. Now, if one full revolution is 2 pi radians, what fraction of the circumference corresponds to an angle theta? Now, if this entire revolution, okay, this doesn't look like a circle, this looks like an egg, and we don't want an egg. Okay, so if this entire thing was 2 pi, right? So I'm saying that this entire thing is 2 pi. Now, so if this entire thing is 2 pi, then what corresponds to this theta, right? This entire thing was 2 pi r. So this must be theta upon 2 pi into 2 pi r, right? We're talking about this part only, this length, this arc length. So see, if we just get rid of our 2 pi's, we will be left with r theta is equal to arc length, which is s, right? And hence we derive our formula s is equal to r theta for the arc length. For what angle? For angle theta, where theta is given in radians. This is extremely important. This formula will only work if your theta is in radians, and this is a very famous formula for arc length. We didn't memorize it, we discovered it. Now, this formula only works when theta, like I said, is measured in radians, not degrees. Radians were invented so mathematics could become this clean. S is equal to r theta. Now, if radius is 10 and angle is 90 degrees, let me say if this is 90 degrees, right? So 90 degrees corresponds to pi by 2, right, in radians. So put this in here, so this becomes pi by 2 times 10 gives you 5 pi. So that's the arc length. Yeah, that's the arc length for a radius which is 10 centimeter and angle for a quarter circle, right? And now let's see. So this is 90 upon 360 into 2 pi r. R is 10, right? So this is 1 upon 4. This is 2. So this becomes what? This is 5. So again, you get 5 pi. But you did a lot of work here. But if you were given an angle in radians like pi by 2, and if you had the radius of the circle, you can just simply get this arc length right away in a very, very clean format, right? So easy. Now you understand something most students never realize. The formula isn't wrong. The unit is wrong. So now, so this is going to be 5 pi centimeter because we are talking about length. Okay. So never put radians or degrees here with pi. This is now a length. Okay. Something approximately equal to greater than 5, something approximately greater than 5. Now, for the sector area, similarly, so the proportion, so if we are talking about this proportion, right? So this is the sector. Oh my god, wait. So this is theta radians. We want to find out this area, right? If I want to find out this area, so this is theta by, so this is theta by 2 pi fraction of the circle or the proportion of the circle, and the formula is pi r square. So 1 pi cancels this, so we are left with half r square and then theta. So this is the formula for the area when theta is given in radians, right? As simple as that. So these are the two most important formulas in your circular measures. S is equal to r theta and A is equal to half r square theta, where both the thetas is in radians. Okay, this is extremely important, right? Now, I've marked enough papers to know exactly where students lose marks, and of course, we go through a lot of examiner reports on a daily basis. So if the radian is 12 and angle is 120 degrees, for arc length, the student writes, so theta is equal to 120 degrees and radius is 12. So in order to find the arc length, they would just multiply 120 with 12 and mess it all up, right? 1440. Okay, very good. I mean, it doesn't even make sense to them that if the radius is 12, right, and this happens more than you would imagine, right? So let's say they're seeing that this is 120 degrees. So if this is 120 degrees and if this is 12, how can this be 1440 centimeters? Like, doesn't make sense, right? So you have to first, in order to apply this formula of r theta, you have to, so this was theta and this was r. This theta is always in radians. So 120 is going to be 2 pi by 3, right? Recognize the famous ones, right? Multiple of pi by 6. So multiple of 60 degrees, which is pi by 3. So 2 twice of 60, which is twice of pi by 3. So 2 pi by 3 times 12. So this is going to give you 8 pi centimeter, right? So this length is not going to be 1440 centimeter, rather 8 pi centimeter. Okay. Now trap number 2 is that you are doing circular measure. You have to use the formulas in radians, but or maybe if you're using trigonometric ratios, you are not you're not putting your calculator in the radians mode, like I said earlier in this lecture, and you keep on finding the values for your trigonometric ratios and you're just messing it up, right? So calculator mode does not change mathematics, radians are still required. Okay, so you will put your calculator in the radians mode, and then you will do circular measure and trigonometry questions in which the domains are treated in radians rather than degrees. If they are in degrees, then fine, put it in the degrees mode and keep doing that, right? Now, using decimals, you never write 1.047 for pi by 3, right? If you have pi by 3 as the angle, just do not write non-exact forms when you already have an exact form which you can use later, because of course precision always matters, right? You would rather have exact values than approximated values, right? Now, another trap is that you do rounding prematurely. You did not take this into account. You just treated this as 1.05, and then in the later stages you started using 1.05, and now the result of this rounding off is getting amplified in the later results, and your final outcome is going to be a lot deviated than the preferred, more precise answer that is required and should be required, right? Now, sometimes the students also mix formulas. So for arc length, they would use half r square theta, which is absurd. And for area, they may use r theta because, they would just say that, oh my God, this is so confusing. This is not confusing. If anything, you can go back to your old definition that this is nothing but proportion. So there are 2 pi degrees. We are talking about sector which has theta degrees, and the formula for the area is pi r square, and for the circumference is 2 pi r. And from here you can derive both the formula. So this cancels this, so this is arc length, and this not this. This cancels this, so this is half r square theta is area. So this is as simple as that. So if you know the derivation, then you must never, the chance of you making such errors become approximately equal to 100 degree. Okay, so there is no chance. Now, there is one more thing. So whenever you are finding out area, your unit, whatever, whether that's meter or whether that's centimeter or whatever, must be in square, because area of a square, the unit of a square is already in a square. And for length, this is power 1. Okay, so it has linear units, it has squared units. So lengths have linear units and areas have squared units. Okay, so this is very important intuition. Now let's if you are given a radius 8, I want you guys to pause the video. So radius is 8 and angle is 5 upon 6 pi. So you should right away know that they're talking about radians, right? So if you're asked to find the arc length, you should simply do r is 8, theta is 5 upon 6 pi, as simple as that. So 20 upon 3 pi. Okay, centimeter if the radius is in centimeters. Now if radius is 7, angle is 2 upon 5 pi, so the sector area must be 49 upon 5 pi. Try to put the area formula and arrive at the same answer that I am. Radius is 7, I'm saying angle is 2 upon 5 pi radians, and area is going to be 49 upon 5 pi. I want you guys to put it in the formula and verify that this area has to be in this centimeter squares, okay? When the radius is in 7 centimeters. Now find theta. I want you guys to find theta given that area is 18 centimeters square and radius is going to be 6 centimeters. Now this is pretty simple. Area formula is half r square, r is 6, theta we don't know, so we let it be. So this becomes 36 upon 2, so theta is nothing but 1 radians, as simple as that. Okay, now This is beautiful connection to the definition that we did at the very start of this chapter, of this lesson. Now notice how everything we've studied connects. Coordinate geometry connected to circles, circular circles connected to radius is going to connect with trigonometry, and in trigonometry the graphs, we are going to study the graphs of y equals to sine x, cosine x. We are also going to do the graphs of y equals to tan x, all of that, right? And they only behave naturally because x is measured in radians, right? Now, we are going to do the differentiation later in calculus, which also depends on radians, by the way. So radians aren't just another chapter, they are the language of higher level mathematics. So make sure that you are keeping this idea about, or this notion about radians very clear in your head. Now, so in this lecture we've done something I wish every textbook started with, that we didn't memorize s, and most of the sorry, I don't wish, a lot of textbooks, they do the derivations of these formulas, which is s is equal to r theta and a is equal to half r square theta. We proved them as well. Now every question in this chapter becomes much easier because you know where the formulas come from. So go to Papa Cambridge, download a question from the topicals, 9709 AS Math P1 circular measure topical past papers. Put this command in your Google search bar, download the PDF and start doing questions. In a few minutes I will be pasting some questions here and start solving them for you. Okay, now so if this lecture is changing how you think about radians, then I wish that you subscribe to the channel and share this with another student who's appearing for 9709 P1. And okay, so let's start with our past paper questions. Okay, so far we have derived every important formula in this chapter, which is arc length and areas. Now let's see how Cambridge actually uses them, right? Now notice something, this question doesn't say find the arc length. Okay, there may be one more important formula in this one, and let me do it very quickly, which is sine rule for area. So if you have a triangle of side A and B, and this is theta, then area of this triangle is half into A into B into sine theta, where theta is in radians. Okay, now, so if I'm asking you to find me this area, we will come back to this past paper question again. So if this is O, this is A, this is B, then definitely this is R, and this is theta in radians. So the area of this sector, sorry, this is B. So area of this sector is going to be half r square theta. This is going to give me the entire sector, but from here I need to subtract this area, right? And this area is going to be minus half r square sine theta, right? Which is right here, because this is A, this is B, just like we had an A here and a B here. So now I can take half r square common. So this is going to give me theta minus sine theta, where this sine theta definitely has to be in the radians mode. And this is going to give me this pink area right here. And I'm going to shade it again so that I can distinctly mark it for you, or let me shade it with black. So we wanted this area. So this area is right here. Okay, now let's come back to this question. Now, so we have two circles, right here. So we have a circle with center A and we have another circle with center B, C. So first of all, let's make some identifications right away. So if this DEB is a tangent, therefore it has to connect, and we did this in the last chapter, that the radius intersects the tangent at 90 degrees. So this definitely has to be a 90 degrees. AC is a radius of circle with center A, then AD must also be the radius. So this is 5. If CB is 8, then this length EB ought to be 8 as well, right? We don't know DE, so we will just put an X here. However, we can find out this X because this right here is a right angle triangle. So if this is 13, this is 5, then by Pythagorean triplets, triples, this is 12. So if this entire thing is 12, then x becomes 4, and you can put the Pythagoras theorem and do it for yourself. So this DE right here is going to be 4, and this is 5, and this is 8. Okay, so we have not solved anything yet. Now see, they want you to find the perimeter of the shaded region. So the perimeter definitely needed this thing, which we already found out. Now the second thing that it wants is this arc length. So for this arc length, we must have this radius, which we already do, which is 8, but we don't have this angle. And how do you find this angle? You're going to find this angle using sine theta is equal to 5 upon 13, and this theta ought to be in radians. So put your calculator in the radians mode. So theta is going to be sine inverse of 5 upon 13, whatever that is going to be. So this theta value, you plug in the formula, which is S is equal to R theta. R is going to be 8 into theta, which is sine inverse of 5 upon 13. And here you are going to get the value for EC arc length. Similarly, you will find out this arc length, which is DC, and you're going to do that through. So this is going to become, so this theta is going to be, the yellow theta is going to be, so cos theta equals to adjacent, which is 5, over hypotenuse, which is 13. So this yellow theta is going to be equal to cos inverse of 5 upon 13. So this arc length, yellow arc length, is going to be equal to R theta, which is 5 times theta, which is cos inverse of 5 upon 13. And make sure that you are putting your calculator in the radians mode, right? So take a screenshot, solve it yourself, check the answer in the marking scheme, and this is how you're going to get the answers, right? So all you need to do is just plug in the values in your calculator and get the answers. I'm not going to do it here, and neither do I have a scientific calculator, nor do I have any inclination to solve these baby steps for you. You guys are, I'm pretty sure you guys are good enough in doing that, okay? All right, so the second part of this ought to be find the area of the shaded region. Now, in order to find the area of the shaded region, what I will do is I am going to find the area of the triangle ADB, this entire triangle. So that's going to be half into base, which is 12, into height, which is 5. So that's nothing but 30 centimeter square. If these are in centimeters, yeah, that's centimeters. So this is 30 centimeter square. And from here, I'm going to subtract this area, which is this red area, is going to be half R squared theta. Theta we saw was sine inverse of 5 upon 13. So this is going to be the red area, which we are going to subtract from the total area, which was 30. And we are also going to subtract the green area from here, which is going to be half R squared theta. Theta was cos inverse of 5 upon 13. And make sure when you are doing these values, your calculator is in the radians mode. I cannot stress enough, right? So this is what it is. So I mean, you can score these 5 and 3 marks for areas, or 4 marks for area, these 9 marks in just under 5 minutes if it comes in your paper, right? So the shaded region was built from shapes we already knew. So this shaded region was built from this triangle, this sector, and this orange sector. So we just took the complete area, subtracted this, and then subtracted this, and then we were left with this green area. So that's very easy. You know it already. I just helped you think. Right now, think about what just happened. We didn't use one circle formula. We used ideas: radius, tangent, right angle, trigonometry, radians, arc length, sector area. That's exactly how Cambridge writes its papers. Chapters don't exist inside the exam. Relationships do. Okay. Now, we are at the, so we have been able to cover this entire chapter in this video. So if you have watched this far, you have probably realized something about the way I teach, right? So in these 40 minutes approximately, I don't teach students what to memorize. I will not do the baby steps for you. I teach them why the mathematics work and the creativity behind it, right? Because once you understand the logic, the formulas stop feeling like formulas. They become obvious. That's exactly how we teach inside Easy Taleem as well, the very channel that you're at, right? So every lecture starts from first principles, then moves to examiner thinking, then finishes with genuine Cambridge questions. So whether you're preparing for October, November 26, or you are resetting for those which are offered free of cost for because of the papers that got leaked, or you are preparing for May June 27. For AS level or A2 level, our programs are designed to take you from understanding concepts to consistently scoring A grades, hopefully. Alongside the recorded lectures, you'll get live classes, worksheets, topical practice, regular tests, past paper discussions, doubt solving sessions, 24/7 WhatsApp access with me, everything structured around the Cambridge syllabus. So, if you're serious about improving your mathematics rather than just surviving the exam, we'd love to help. My direct WhatsApp is at +92 329 302 8485 if you want to have a one-on-one discussion. And on Instagram, you can follow us at Easy Taleem. We go by the name of Easy Taleem, EASYTALEEM, same example, same spelling. If you don't join us, keep following this YouTube series. Every chapter remains free because good mathematics should be accessible to every Cambridge student. In the next lecture, we'll begin one of the most important chapters in AS mathematics, which is trigonometry. And while students, so this is an unpopular opinion, but I love this topic: the graphs, the connection with the quadrants, the unit circle, the um, the equilateral triangle, the isosceles triangle, deriving the values or the multiple of values for the triangles. So you'll finally understand why everything we have learned so far, from functions to circles, leads naturally into circular measure. It all leads naturally into trigonometric graphs, identities, and equations. Until then, take care, keep practicing, and I'll see you guys in the next lecture.